Hi guys, this is Mrs. Gastler, and in this video we're going to talk about rotational kinetic energy, okay? But we're going to start by talking about linear kinetic energy, or sometimes they call it translational. Translational. When you see the word translational anywhere in the AP test or textbook, they're talking about motion that goes in a straight line, so that's linear. And then when they talk about angular or rotational, they're talking about things that go in circles, okay? And then there's circular, which is things that are going in circles also. These are things that are spinning, so there's straight line, spinning, and going in circles, okay? So then we'll get to the angular here in just a second. Okay, so we're going to start with linear. Linear kinetic energy is 1/2 mv squared. That equation is in your equation sheet. And if we look at this particle, we're going to start with one particle, okay? That one particle going around this circle it's going to have an angular velocity. So, and that equation is also in your equation sheet, v equals r omega. And so we're going to just take this velocity and we're going to just stick it in there real fast, okay? So we're going to have 1/2 m r omega squared. And now we're just going to do a little bit of quick rearranging. So we're going to have m r squared omega squared, and you might maybe recognize this right here as I, okay? And once we've done that, we've just found what rotational kinetic energy is. It is 1/2 I omega squared, which shouldn't be a surprise to anybody, right? Because we really just take the rotational quantity, rotational equivalent, and kind of replace them. That's been the name of the game so far, right? And look at that. That's just exactly what we did here too, okay? So that's for one particle, so right? So our particle. Okay, so what would we do if we were looking at the rigid body? Remember we talked about the rigid body. All that, if this, instead of being a particle going around a circle, if it were a solid object going in a circle, the whole thing is rotating, then what would we do? Well, we would just do the sum of all the particles, right? Mr squared, like this, times omega squared, okay? But you might remember this is that that rotational inertia of any object, right? And so we have, what do you call it, a chart that has a bunch of how you find the rotational inertia of a bunch of things. And if you're in AP Physics C, you get to do this one, right? R squared dm. So you might have to be doing that when you do this, but so it would just be 1/2 I omega squared, but this could be any object, okay? So it works for a single particle and it works for any object. So let's take a look. What if we have an object is it's moving translationally and in a circle at the same time, so it's rotating. So this might be something like, there's our surface. Maybe we have a disc, like a tire or something, and it is both moving this way and it's also rolling like that, okay? So it's rolling. We're actually going to have a whole thing about rolling later, so we'll worry about that later. But for a disc, in case you don't have that one memorized yet, it is 1/2 mr squared. So that one's actually kind of an easy one, okay? When we find the kinetic energy total, we're going to have to account for the fact that it has the translational kinetic energy and the that's an R, K, rotational energy, but sometimes we write KT equals KTR plus K rot, okay? Because nobody wants to write all that out, right? So let's see what our formula would look like. Well, we'd have 1/2 mv squared plus 1/2 I omega squared. And so what we often do is we kind of do this same sort of thing that we did up here to show what the angular rotation or the rotational KROT, there we go, kinetic energy looks like, but we're going to kind of work backwards now so that we can get it in terms of what we know. Maybe we know it has a mass and we know how fast it's going this way, but we also know that it's rolling, okay? So we'll leave the 1/2 mv squared, okay? but we'll keep the 1/2, and now we'll just put this in there, right? So 1/2, and I'm going to go with a little m and a little r, because I know how big this is, r, okay? Squared. And then omega, remember v equals r omega, so omega would be v over r, yeah? Okay, so this will be v over r, but if I distribute that squared, it'll be v squared over r squared, like that. Which is really nice, because then my r squared goes away. So this is just 1/2 mv squared plus, I've got 1/2 times 1/2, which is 1/4 mv squared. 1/2 mv squared plus 1/4 mv squared is 3/4 mv squared. So the total rotational kinetic energy is the rotational kinetic energy that it had because it's moving this way, plus a little bit of extra because it's also rolling. So that's what we do with rotational kinetic energy. Thanks for watching.